everybody. My name is Alvarius. I'm an on-chain developer, mostly focusing on fully on-chain games. And today I'm going to tell you a story about how we built our first fully on-chain game and made a big mess, and then built a framework that now allows us to build full on-chain game prototypes in a matter of a couple of days. But first, let me take you back to around 3.5 years ago. 3.5 years ago, my friend Justin and we discovered Dark Forest, and we got really inspired by it. Dark Forest was one of the first fully on-chain games, and that means basically all the game mechanics, all the physics of the game are deployed or are living in smart contracts on a public blockchain. And then the client is essentially just a window into this on-chain world. And now you suddenly have something where the world will essentially live on as long as the chain will live on, which makes it feel very real. And then also the other thing is you're deploying to a public global computer where also everybody else can deploy to the same computer and extend the world. So there's a lot of potential for emergent behavior here. And we had this feeling that there's this potential to create something that can be more meaningful than existing virtual worlds. Of course, just the potential, you still have to build a fun game. And so we got started building. We got started with the default patterns that everybody was using at the time. So the first thing we wanted to add was positions for our entities in the game. And so we added a mapping on the contract and then also a mapping on the client because, of course, we want to render the entities, the position of our entities in our client. And then we had to add a couple of getter functions so that our client, when the client loads, can basically hydrate the initial state on the client. And then we added the first physics of our game, the move function. And in here, we have to make sure to both modify the state, but then also emit an event that the client can listen to keep the state in sync. So this is a lot of boilerplate just for having one type of state synchronized between contracts and clients. And of course, we don't only want position, but a lot more on-chain state. So the next thing we added was health for our entities. But now we had to add the exact same boilerplate again. Mappings, getter functions, custom events, custom sync stack on the client. And then the same thing for energy, and for skills, and for inventory. And you get the idea. It's the same boilerplate over and over again. And at some point, we were at the point where we couldn't really iterate on the actual game mechanics anymore, because every time we wanted to change anything, we basically had to drill that change through the entire sync stack just to keep the contract and client state in sync. And so at some point, we decided to trash everything we have and change something. We decided to build a framework to solve our own problems so that for the next project, we could basically skip all the boilerplate and just focus on the fun stuff, on the game mechanics of our game. And that framework over the last 3.5 years turned into mud, and now we're not the only ones using it. Now it's used by a bunch of teams, from small teams to big teams, who all ran into the same problems that we ran into, and now they use mud to ship faster. So in the next 15 minutes, I'm going to talk about 3 problems that we ran into back then and how we solved them in mud. The first one I already told you about. On-chain games have a lot of state, and you need to synchronize that state to the client to render a game. And I also already told you about the fact that the default approach of using getter functions, events, and so on doesn't scale well. And so here's what we did. The first thing we did was standardize the way we basically shape our state. And so now we just use tables for everything. A table, you can kind of think of it as a mapping in Solidity. You can implement it as a mapping in Solidity. But we like to think of it as tables. And tables can have multiple rows. We call those records. And then each record is uniquely identified by one or more keys. And now the important thing is what happens when a record in our table changes. Well, instead of emitting a different event for each different type of table, like position changed, health changed, and so on, we emit one default event, one generic event for all the tables. And on that event, we have enough information to know which table changed, which record changed, and which value in that record changed. And then with this generic event, we can then build a sync stack that understands this generic event and then takes care of updating the same value on the client. And now we don't need we don't need a custom sync stack adapter for every different type of table, but we can reuse the same code for all the different state that we have. And then we generate some libraries for the contracts that basically just take care of setting the state and then also emitting this event, so we don't have to think about that every time. And now we essentially eliminated all the boilerplate, because now adding a new type of state is just one line of code on the contracts. It's automatically synced to the client, and then one line on the client to access the state there. And then once we have this automatic sync stack, we can do more fun stuff with it. Like we can also pipe the state into a relational database from which then the client can use it to sync the state quicker. So we now also have an automatic indexer. And because now all the state lives in a relational database, we can also use SQL to basically query all of our on-chain state. Now, some of you might have noticed that Solidity doesn't actually have generic events, so we have to use a little trick here. What we do is on the contracts, we basically encode the state as tightly as possible, and then we emit that encoded data as bytes on the event. So our event signature is just bytes everywhere. And then on the contracts also, we have a special table which stores the schema of all the other tables. And this table is also synced through the default sync stack. And that means now the clients and indexers have the information that they need to then decode the state update. And all of that is encapsulated in this automatic sync stack, so it all happens automatically. I have a little demo for how this looks in practice, and I think I have to, yep. All right, so here we see a client. On the left side, we see a default app of MUD, a counter. Every time we click the button, a transaction is sent. On the right side, you see the World Explorer, you can see the transactions. And then what happens is in the background, the sync stack basically synchronizes the state from the contracts back to the client, and that's when the UI updates. And the other thing you can see here is in the World Explorer, there's also a view to basically inspect all the data in your app, because it's all standardized in tables. And then we can look at another quick demo, which is a slightly more complex table, a task list. And here we can use SQL input on the World Explorer as well to basically filter down the task list to only display the tasks that have been completed or not completed yet. And obviously, you could also use more complex SQL here. All right, so that's the core of it, but it doesn't end here. The next problem we ran into is logic. On-chain games also, besides a lot of state, they also have a lot of logic. So the next issue we ran into is the 24 kilobytes bytecode limit on contracts. Here's how we solve it. The general approach is very similar to the diamond pattern. So we have one central entry point, which we call the world contract. And then into that contract, we register stateless system contracts that basically implement the functionality. And then when a user calls the world contract, they only need to know the address of this one world contract. And then the call is forwarded to the system contract. So far, pretty standard diamond. But now we can add the store to it. In the store, we have a table for the systems. So now when we register a new system in the world, information about the system is also stored in the systems table. And now the automatic sync stack can take over and basically mirror that information into a database. And then from that database, we can generate an API, which is always up to date. So when we register a new system, that also gets registered into the systems table, and then the API immediately updates. Now, I told you that systems are stateless, which is true, but they can still interact with state. They can read from tables, and they can also write to tables. And then that data is also, again, automatically synced to the client. But because the system contract itself doesn't contain any state, we can very easily upgrade it. It's really trivial. We literally just swap out the implementation address, and we don't have to take care of storage slots ordering or whatever, because the system contracts themselves totally stateless. All the state lives in the store in the world. And then when new tables are registered and runtime later, those are also picked up by the automatic sync stack immediately. And each table has its own storage position in this contract, so there's no state overlaps or storage slots overlaps. And with that, we can then take it one step further and introduce the concept of namespaces, which basically means a system that is registered in a namespace can read from all the tables, but can only write to the tables that are in the same namespace. And with that, we can now really lean into extendability, because we can basically allow anybody to register new functionality in our world contract. All right, another quick demo. We see, again, the counter table, and now we see the Interact tab in the World Explorer, which basically shows all the functions available on the world, including the one that increments the counter, and we can also interact with the world through this Explorer. And now when we add a new function, another increment function that adds 2 to the counter, we save that file. In the background, it's immediately upgraded through the dev tool, and then the new ABI function immediately shows up on the World Explorer, and we can again use the World Explorer to interact with the app. All right, last one for today is higher level logic. You may be familiar with ERC20 and the approve and transfer from functionality, which basically, among other things, it allows you to give somebody permission to transfer on your behalf, which, among other things, enables atomic swaps. So pretty cool. Now let's say we want to add that to our game. We want to allow somebody, we want to give somebody permission to move our unit on our behalf. Now we could add an approve move function and a move from function. And then when we want to do the same for attacking, we could add an approve attack and then attack from function. But that would, again, be a lot of boilerplate. And now let's say we wanted to add something very similar but slightly different. We want to allow somebody to sign a piece of data that then allows us to attack or move on somebody's behalf. So should we add move with signature, attack with signature? Because we have a framework now, we can move that logic one level higher to the level of the framework, and then we don't have to implement it in each of the systems. So in our case, we can add a new entry point to the world, which is called call from, and it takes another argument in addition to the system arguments, which is the address that you want to call, on whose behalf you want to call. And then this entry point can implement the functionality for checking that this delegation is actually valid. And then if it's valid, it forwards the call to the system with this new address that you're calling, on whose behalf you're calling. And then with that, we don't have to implement that for every system again, but rather it just implemented once at the framework level and works for all the systems. And same with the signature example, we have a call with signature entry point here, where you can call it with a signature from somebody that allows you to call a function on their behalf, and then if it's valid, it's forwarded to the system as them, basically. This is useful for a bunch of different things, but one example is session wallets. So in our game, we don't want an approval pop-up every time we do anything. Not demo time yet. We don't want an approval pop-up when we do anything, but rather we want to create a scoped delegation once at the beginning, and then the user should be able to, for the duration of the session, to just do moves in the game without additionally approving. And in our case now, we can connect the main account, we can create the scope delegation through this entry point function, and then, user doesn't have to click approve every time again. And we have, again, another quick demo of this. This is using some UI that ships with Mud. Here the user can create an account or connect an existing account. In this example, we're creating a passkey account. Then a delegation is set up, and then once that is set up, the user can basically move in the game without additionally, clicking approve every time again. This is a demo app we built to demo this onboarding flow, but then also some latency stuff that we worked on. You can try it out if you want on your phone on eatthefly.com. And yeah, this was just a tiny glimpse into Mud, which we built in the beginning to solve our own problems, but now is used by many people who had the same problems. Many of them are going to present tomorrow at Mud Day here in this venue at Classroom A. So I would recommend to come check that out if this was interesting to you. And then if you can't make it tomorrow or just in general, you can also learn more about Mud on mud.dev. And with that, thank you, and hopefully see you tomorrow.
Good stuff. I don't know if I'm a frog or if it's lunchtime, because that made me hungry. Cool. So the first question from the Q&A is that in your demo, transactions are happening instantly. In Redstone, block time is 2 seconds. What's going on there?
Yes, so that's some new instant confirmation stuff we worked on. We're gonna talk more about that tomorrow at Mud Day. So yeah, I don't wanna reveal too much. So I would recommend to come to Mud Day tomorrow.
Very interesting. Next question. How do you handle a table growing beyond the size of one storage slot?
Okay, that might have been unclear in the way I explained it. Tables can grow indefinitely big. You can basically, one table, the table can have multiple records, and the records can span multiple storage slots. So there's no one storage slot limitation. You can have the schema has some limitation in the number of fields you can have. I think it's 28 fields. And then one table can have multiple records, as many as you want, and that just is linear in storage, so you can go on as much as you want.
Okay. So how does Mud sync table schema changes for relational databases and ensure that there are no issues? What happens if that schema migration does not work? That's
a great question. You can't currently change a schema. So it's basically you register a table once, and then that's the schema that you will have. If you need to change the schema, you can create a new table. In theory, it would be like doable to add fields to your schema, but yeah, like with the mentioned complications, you would have to do a database migration as well, and that's not trivial. So we decided to just make schemas immutable.
Cool. How were namespaces implemented in the EVM?
I don't know into how much detail I can go here, but it's basically just like contract logic. Like we have access control logic in the vault contract that makes sure that you can only write to tables that you have access to. Oh, maybe one thing that I didn't mention that might make this more clear. If a system is registered in a namespace, then what happens if the user calls the vault entry point is the vault doesn't do a delegate call to the system, which a normal like default daemon would do, but rather it does a call. And then when the system wants to read or write from the table, then it basically does a call back to the vault, and at that point we can do access control on the namespaces.
Okay, I think this is the last question in the queue. What do you think about the possibility of building real-time multiplayer games using new existing infrastructure projects that provide TEEs, trusted execution environments, while using MUD to store the incremental changes to save costs?
Yeah, this is also a great question. Again, I would recommend you all to come to MUD Day tomorrow. There's some demos there that kind of do something in this direction. It's a real-time game, slightly different approach, but yeah. Definitely possible to do real-time games at this point.
This is the same talk tomorrow, right?
It's in Classroom A tomorrow. I'm not sure what time exactly. I think 11 until 5 or something.
Okay, Classroom A if you want to hear about when they do immediate stuff with TEEs. Okay, we got one more question. Game dev is often on the tech frontier. What lessons do you have for the rest of the industry?
Yeah, so we started this framework as a way to build our games more efficiently, but as we built this framework, at some point we realized there's nothing in this framework that's specific to game dev actually. So yeah, if you're building an on-chain app that's not a game, I would recommend you to just try it out as well, and it might just make it easier.
Okay, and I think we got time for one more question. Why do we need to bring everything on-chain, and how does this scale moving forward for FPS games?
Yeah, this is almost a philosophical question, like why do we need to bring stuff on chain? There's a lot of advantages, or like a lot of things that are interesting about it. What I mentioned in the beginning, you have something that can potentially live on forever. You have the potential for other people to extend it in more interesting ways because they can deploy code to basically the same computer that this game is running on. In terms of scalability, that's kind of what we're working on, and also a lot of other people are working on. I think it's interesting to try to push try to put more ambitious things on chain to basically extend what we can do on chain to kind of remove those limitations.